In this video about consumer products and energy from fuels, we want to start talking about topic 2 from Unit 2 in National 5 Chemistry. And we're going to start with the consumer products part because it's quite closely linked to the homologous series topic, which we've just finished in the previous videos. So we'll leave the energy from fuels part just now. So before we get started on talking about even more homologous series that are found as consumer products and what that means, we need to remember what a functional group is. So functional group is a term that came up in the last topic too. And it means a group of atoms, or a single atom, but usually a group, that indicate what homologous series is present. So based on what those atoms are and how they're bonded onto the compound, we can tell what type of molecule that is, what homologous series it belongs to. So for example, if we find a hydrocarbon molecule and it contains a carbon-to-carbon double bond, we know that that is an alkene based on this functional group, because that tells us, that indicates that it's an alkene. So it's like a tag, if you like a name badge for the molecule. It tells us what type of molecule is present and therefore what series it belongs to. So what we want to do really in this topic is just add on a couple of extra homologous series. We want to address a couple more that are different because they are consumed within society for certain purposes. They're used specifically in certain roles and certain reactions that are important to the consumer as a product. And the first that we're going to start with is a group of chemicals, a homologous series called the alcohols. Now, of course, alcoholic drinks have been known for thousands of years. Many people use alcoholic drinks to celebrate social occasions, or whilst other people don't drink alcoholic beverages at all. Now, there are many different alcohols, but the alcohol present in alcoholic drinks is a specific alcohol from the alcohol homologous series. But we'll get into that a little bit later. So, what do we need to know in terms of our chemistry for the alcohols? Well, they contain a functional group, and that functional group is called the hydroxyl group. So anytime we see this oxygen bonded to a hydrogen and the other bond of the oxygen joining on to a carbon chain, we know that we're dealing with some kind of alcohol because it has this hydroxyl functional group. Okay. So for example, here is a molecule, and by looking at it, the first thing we can tell is it is in fact an alcohol because it has the OH functional group and nothing else in particular for this particular molecule. But of course, we want to be a bit more specific than that. We want to be able to name this accurately so that we know which alcohol it is that we're dealing with. Because as I said, there's many different types, many different isomers of different types as well. So we want to use our same systematic naming rules that we have used previously. We want to, first of all, select the longest chain that includes the OH group. Then we want to number from the most exciting end, of course. This time we know that we're always looking for functional groups. They are the most exciting things in a molecule. They're usually the parts that do the reactions. Then we want to name and number any branches. And then as an additional rule that's slightly different from the other homologous series we've looked at, we want to indicate the position of the OH group. We want to indicate where the functional group is in the molecule. But hopefully you'll remember doing that for the alkenes, because when we had, for example, a butene molecule where the double bond started on carbon 2, we couldn't just call it butene, we had to call it but2ene to show where that double bond was. And it's the exact same with the alcohols and the OH functional group. We have to indicate whereabouts in the molecule it is, based on what carbon it's bonded to. So let's go through each one and see what we come up with for this molecule. So first of all, longest chain that includes the OH group. In this case, it's very simple, it's very easy. There's only one chain here. Longest continuous carbon chain, and there it is, 2 carbons. And thinking back to our prefixes, we know that if we have 2 carbons, the eth prefix is going to be used somewhere in naming this molecule. So we've done the first part. Second part, number from the most exciting end, which means the side with the OH group. Of course, that's here, because the OH group starts with this carbon here. It's bonded to this carbon. So this carbon is carbon number 1, and this carbon is carbon number 2. So that is our numbering done. Then we have to name and number any branches. Well, in this case, it's very simple. We have no branches, so we can skip that step. And then we want to indicate the position of the OH group. Now, in this particular molecule, it doesn't really matter because I could have bonded this OH on this side or on this side. But either way, it would just end up being a mirror image of each other. So it doesn't actually matter, it would give me the same molecule. And it's not an isomer because it would be the exact same molecule just flipped over. So in this case, I don't have to indicate the position of the OH group either. So this is just simply Eth, because we have 2 carbons, and then we always end our alcohol names with ol to show that it's an alcohol. So this is ethanol. And this in particular is the alcohol that's used in the alcoholic drinks and beverages that I mentioned earlier. So let's make it slightly trickier and let's see if we can apply those same 4 rules to slightly more complicated molecules. So clearly, this next molecule is still an alcohol. How do we know? Because it contains our hydroxyl functional group, so it's definitely an alcohol. First rule, we have to identify our longest chain of carbons. Here they are. There are 3, so this is some kind of prop something, because we know that that is the prefix for 3 carbons. We then have to number the carbons based on the most exciting end, which is where the hydroxyl group is. So that's going to be starting at the right hand side again. It's 1, 2, 3. And again, there's no branches here, so we can just go straight to step 4, which is to indicate where the hydroxyl group is. Now in this case, it does make a difference where it is, because if we take off this hydroxyl group and put it somewhere else, that will have to be done by breaking bonds. We can't just flip the molecule over, right? It would have to be moved by breaking bonds. So we have to indicate where this hydroxyl group is. And the way that we do that is to say, yes, it's propanol, but because the hydroxyl group is on carbon 1, we say it's propan 1 ol. And that 1 between the 2 dashes, because remember, whenever we use numbers in our systematic naming, we have to separate them from the letters with dashes. That 1 shows me which carbon the hydroxyl group is bonded to. So we have propan 1 ol. But what if that hydroxyl group was found somewhere else? Well, if we look at this molecule here, longest chain again is here. And once again, we have 3 carbons, so we know this is also some kind of propanol because we've got another hydroxyl group here. But this time, it's bonded to this central carbon here. So in numbering the longest chain, we can actually go from any side that we like because it's an equidistant move to get to the middle. So we can go 1, 2, 3, or we could have went 1, 2, 3 as well. It doesn't matter because the functional group is in the middle. But what does matter is that we show where that functional group is in the overall name. And of course this time, because the hydroxyl, which makes it the alcohol, is bonded to carbon 2, it has to be propan 2 ol. And again, there's no branches here, but if there were branches, we would just use our same systematic naming rules to add that information at the start of the molecule's name. Now, just a couple of key points to point out here about drawing and naming these molecules. Remember, at National 5, if we are drawing full structural formula, which we are in this case, we have to show all the atoms and we have to show all of the bonds. So in some cases, you may see a hydroxyl group written as OH like that. I would avoid doing this because it doesn't show us all the bonding information. We're not showing that bond between the oxygen and the hydrogen. And it also might lead you to make this mistake here. This is wrong. We cannot write this. This is not a hydroxyl group. This just doesn't exist. Because what that implies is that I am bonding a hydrogen and an oxygen by having a single bond to an oxygen and 2 bonds to a hydrogen. Based on what we know from Unit 1, that does not work. We can only have one thing bonding to a hydrogen and we must have 2 things bonding to an oxygen based on their valencies, based on where these atoms are in the periodic table, so we can't do this. It has to be oxygen with 2 bonds and hydrogen with 1. So it's always the oxygen that bonds to the carbon, it is never the hydrogen, because then we couldn't add that oxygen on. So always show all the bonds, show both lines, and that hopefully will help you avoid making that mistake. The other thing that I would point out here is that you will often see not just the full structural formula for consumer products, but also the shortened structural formula. And all that means is we take each carbon and we write down whatever is directly connected to that carbon by not including the bonds and summarising how many of each atom is bonded to that carbon with a little number. So let me demonstrate that with this molecule here. So if we start from the top one actually, I will now write the shortened structural formula next to this compound. So we know we have a carbon to start, and that's followed by bonding to 3 hydrogens. So the way we write that, it's just as if we're writing a simple molecular formula. C with 3 H's. We then move on to our next carbon and see that that carbon has, okay, it's bonded onto 2 other carbons, but remember we deal with the carbons separately. So we'll just include our next 2 hydrogens. So we have another carbon bonded to 2 hydrogens. We then have a carbon that is bonded to 2 hydrogens again. So let's write that down. And then we have our functional group, our OH. So as you can see, that shortened structural formula in fact looks quite like the full one, except we're not showing any of the bonds. And that really is the only difference. You just have to make sure that you have the correct number of atoms per carbon that you are writing about. Now what is important to notice about the shortened structural formula is that it's not the same as the simpler molecular formula, which just sums up how many of each atom we have in total. So if I just go with this same example here, we wouldn't show each of the carbons in the chain individually, we would just write down that there's 3 in total and that they are bonded to 7 hydrogens. The only thing in this case that we do show separately is the function group, like that. So even though we're repeating a hydrogen, instead of just putting an 8 here, that is important because it shows us again how important this function group is, because that indicates straight away we can look at this even at the molecular formula level and see, yes, it's definitely an alcohol because it has an OH hydroxyl group contained within it. And that brings us to our final point about the alcohols for this video, which is the general formula, because of course this is still a homologous series, and remember a homologous series contains a general formula that all of the compounds, all of the molecules in that series will follow. So if we look at the molecules we've looked at so far, we will see that once again we're using Cn to show, okay, for a certain number of carbons we will then have 2n plus 1 hydrogens, and then again we explicitly show that OH group. So very similar to our alkane formula, we have to, in order to be able to figure out how many hydrogens we need, we have to times the number of carbons by 2 and then add 1 on, and then we have to make sure that we include an O bonded to an H somewhere in the molecule as well. And if we follow that, that means we have formed an alcohol.